In this video, we're going to prove that addition on the rational numbers preserves order. So recall that we take this fact that addition preserves order as an axiom for the natural numbers and the integers. And it's also an axiom that defines an ordered field. And so proving this for the rational numbers is one step along the way of proving that the rational numbers is in fact an ordered field as we've defined them. So let's recall our definition of the rational numbers. If we have an integer m and a natural number n, then the rational number m over n is defined as the set of all fractions p over q that are equivalent to the fraction m over n. And recall that a fraction m over n is equivalent to a fraction p over q if and only if mq is equal to np. Okay, so a rational number is really a set of infinitely many different fractions, all equivalent to that rational number. And then, of course, q represents the set of all rational numbers. Now, with these definitions, we can say that two rational numbers, m over n and p over q, are equal if and only if mq is equal to np. So it turns out that because of our definitions, if mq is equal to np, then the infinitely large set of fractions that are equivalent to the fraction m over n is going to be exactly the same as the infinitely large set of fractions that are equivalent to the fraction p over q. So, in other words, the rational number m over n will be equal to the rational number p over q in that case. Let's also recall the definition of the ordering on the rational numbers. If we have rationals f1 and f2, and we represent f1 as m over n, and we represent f2 as p over q, then f1 less than f2 means that mq is less than np as integers. So we define the ordering on the rational numbers in terms of the ordering on the integers, and of course that's how we deduce trichotomy, for example, of the ordering on the rationals. So that's our definition of the ordering on the rational numbers. Let's look at one more definition. If we have rational numbers f1 and f2, and we represent f1 as m over n and represent f2 as p over q, then the sum of f1 and f2 is given by the standard formula that you learned in grade school, mq plus np over nq. Okay? So that's how we define addition of fractions, just the standard way. So now let's turn to the result we're going to prove. We're going to prove this lemma that if a, b, and c are rational numbers, and if a is less than b, then the sum a plus c is going to be less than the sum b plus c. So let's let a, b, and c be rational numbers. And let's suppose we've represented a as m over n, we've represented b as p over q, and we've represented c as r over s. So in particular, all of the numerators m, p, and r are integers, and the denominators n, q, and s are going to be natural numbers. Let's also suppose that a is less than b. So in particular, we know that m times q is going to be less than n times p. So our goal is then to prove that the sum a plus c is less than the sum b plus c. So with these representations, what we aim to prove is that m over n plus r over s is less than p over q plus r over s. And now let's recall our definition of addition so we can keep our target in mind here. So if we apply our definition of fraction addition, then what we need to prove is that ms plus nr over ns, the sum of a and c, is less than ps plus qr over qs, which is the sum of b and c. All right? And one more thing we need to remember is what it mean for those two fractions to have that order relationship. Well, according to our definition of the ordering, to prove that those two fractions have that particular order relationship, we need to prove that qs times the quantity ms plus nr is less than ns times the quantity ps plus qr. Okay? So if we can establish that last line there, then we'll have proved what we need to prove. Okay? So again, our assumption is going to be that a is less than b, which works out to the integer relationship mq is less than np. And our goal is to prove that qs times ms plus nr is less than ns times PS plus QR. All right. So let's start with the left-hand side. If we multiply through QS in using the distributive property to the quantity ms plus nr, we see we get mqs squared in the first term plus qsnr for the second term. Now we know that mq is less than np, so if we replace that mq in the first term by np, we get a larger value. So we'll get that mqs squared plus qsnr is less than nps squared plus qsnr. Now notice that both terms in that last sum have a factor of ns in them. So we factor that out, we get ns times the quantity ps plus qr, and that's exactly what we needed to demonstrate, that qs times the quantity ms plus nr is less than ns times the quantity ps plus qr. So we've proved the relationship that we need to demonstrate using the assumption that mq is less than np. That is, we've proved that a plus c is less than b plus c, assuming that a is less than b. So that concludes this proof and this video. Thanks for listening.